welcome you all to the first webinar under 21, one of India's most great technical festivals. Welcome to MindSpark. Taking the legacy forward this year too of technical exhibition, and we hope to conduct a successful technical exhibition 5.0.
We hope all of you are doing well in this difficult time. This pandemic has affected all of our lives in almost every aspect. We believe that every difficult situation is an opportunity for innovation, and here at MindSpark, we strive for the very same. On this warm note, we are thrilled to welcome you all to the first webinar of Tech Expo webinar series of the 15th edition of MindSpark. Did you guys know quantum computers can solve calculations at an unfathomable speed, making even the most complex problems with a very high number of factors to analyze look like a child's play? To put this in some perspective, IBM's Deep Blue, the chess-playing supercomputer which took on the world champion Garry Kasparov, could calculate 200 million potential moves per second in 1997. Today's quantum computers are capable of 1 trillion calculations per second.
We deem it as an honor to have Tata Institute of Fundamental Research at Technical Exhibition 5.0's webinar series this year. TIFR has been instrumental in research in sciences such as physics, chemistry, biology, mathematics, computer science, and science education, and has made the nation proud. Quantum computing being the subject of discussion today. Today, we have one such individual from TIFR who is making his contributions in the field of quantum computing.
We are honored to have with us today Dr. Sumeru Hazra from Tata Institute of Fundamental Research, Mumbai.
Dr. Hazra is currently a research associate at Tata Institute of Fundamental Research, Mumbai. He completed his bachelor's from Jadavpur University, Kolkata, and master's from TIFR. He has been a part of team working on quantum measurement and control laboratory since 2015. He works on building hardware based on superconducting circuits for quantum computing and quantum information processing. In addition to his interest in quantum computing, he enjoys painting, photography, and football. We are so honored and equally excited to have such a multifaceted personality with us. Thank you, sir, for taking time out of your busy schedule to address this session. Now, without any further ado, I would like to invite Dr. Hazra to take on our virtual dais and proceed with the webinar.
Over to you,
Thank you.
sir.
Thank you. First, let me share the screen, but this option is disabled. Can you help me with that?
Yes, sir. Just a second.
Sure. Can you see this?
Yes, sir,
Yes,
we
sir.
can.
Yeah. So first of all, I'd like to thank the organizers for inviting me for this talk. It's a pleasure to talk about quantum computing to such a large audience. And I just want to add a small correction. I am not a doctor yet. It's just soon to be doctor. And this I have not submitted the thesis yet, but it's like on the way. So yes, by training, I'm an experimental physicist who has been working on developing the hardware for quantum computers. And I work in the field of superconducting circuits to make such processors. And yeah, so today I'll talk about how you can make a quantum computer using electrical circuits. So let's begin. So first, before we dive like deep into the quantum region, first take a look at the evolution of the classical computers and appreciate how they have evolved over past few decades. So as you all know that the building block of a classical computer is bits. And they are basically, you can think of them like a switch, which can either be in on or off state. So they are at the heart of the Boolean logic, which are behind the operations that you do in a classical computer. And here is the first like programmable digital computer that was ever made, which was known as ENIAC, and where vacuum tubes were actually used for individual bits. And with roughly 18,000 vacuum tubes, it weighed about 30 tons. And here you can see in the picture that an engineer is actually holding one such bit in his hand. And needless to say that over the next few decades, these computers not only became miniaturized, but also like they have become vastly powerful. And today's like a modern day computer contains billions of such bits or transistors inside the central processing unit. And one of the most powerful PCs that we have today can execute exaflop operations. That means it can calculate 10 to the power 18 calculations per second. So this is very powerful compared to what we used to have even a few years back. But is this going to be powerful enough to solve any kind of problem that we might come across? Unfortunately, the answer is no. Turns out that if you want to simulate a real molecule, like for example, if you want to look at the quantum mechanical behavior of such molecules, the complexity of such problems grows exponentially. And beyond a certain size of the molecule, it is almost impossible to solve even with the most powerful of today's computers. So what do we do about it? You must have come across this famous, you must have heard of this famous scientist, Richard Feynman, who actually proposed that, okay, if you want to solve a quantum system, do it on a quantum computer and don't even try to do it on a classical computer. Of course, at that point, at the time, the quantum computer was just a theoretical concept, but it was it could have been theoretically shown that if you had this hypothetical quantum computer, you can actually benefit and solve these kind of problems exponentially faster. This is not just the kind of problem that you can solve. There are several other problems that can be benefited if you have a quantum computer. For example, if you want to search an unsorted database, if you have a deck of n cards and if you want to find one such particular card, for example, 7 of hearts, the way you do it on a classical computer, you have to sort of flip and see one by one. It doesn't matter if you do it randomly or you do it serially. You have to, on an average, look in by 2 cards to find the answer. And if you're really, really unlucky, it will take you all n cards to be flipped before you know the answer. Turns out that the quantum algorithm for the same problem can solve this in square root of n trials. And as the size of this database grows larger and larger, this advantage becomes more and more prominent. So this is just the beginning. With a quantum computer in near future, you can have exponential and polynomial to even exponential speedups, and you can actually use it to solve difficult problems like drug discovery, traffic optimization, financial modeling, quantum chemistry, and many such other problems. So how does quantum computer do it? So in this talk, I'll first introduce qubits, what are they and like how do they work? And then I'll explain why is it so powerful compared to the classical bits. And then I'll explain how you make a qubit physically, like in a physical system. And finally, how you can make a processor using these qubits that I introduced. And to end the talk, I'll discuss some of the challenges that we are currently facing as a community to build a quantum computer. So let's start. So as I already mentioned, that a classical bit can be in either 0 or in 1. But what if you can store information in a quantum state? For example, you can use different energy levels of an atom, and then you have these states 0 and 1 defined here, and then this makes a qubit. A qubit, unlike a classical bit, can be in a 0 state, a 1 state, but instead of, in addition to that, it can also be in a superposition state. What I mean by that it can be simultaneously in 0 and 1. That's amazing. And that's how like interesting and also mysterious how quantum mechanics work. But mathematically, you can represent the state of a qubit like this. where the state of a qubit can be represented with these coefficients cos theta by 2 and sin theta by 2 e to the power I5. And when you measure the qubit, it will produce either 0 or 1. So it is simultaneously dead and alive when you are not looking into it. But as soon as you measure the qubit or measure the state of the qubit, it's going to be collapsed either into 0 or 1. So the cat will either be dead or it will be alive. And notice that the probabilities of finding it in 0 and 1, that they add up to 1. And these probabilities are related to the coefficients that I have written here. So this is a nice representation of a qubit, because now it can be represented on a sphere, which we call a block sphere. And then like you can think of it like a GPS, and each of these points on the block sphere is now a unique superposition state, with the 0 state or the ground state at the North Pole, and the excited state or the 1 state at the South Pole. Now that's all about one qubit. What you have more than one qubit? So suppose you start with 4 classical bits. 4 classical bits can stay in one of these 16 possibilities at a time. For example, it can stay in this particular state 1010. However, if you have 4 quantum bits, it can simultaneously exist in all 16 possible states at a time. And as you keep adding more and more qubits to the system, these possibilities, the number of possibilities grows exponentially. And by the time you have 300 qubits, it can simultaneously exist in 2 into 10 to the power 90 possibilities, which is a number larger than the total number of atoms in the universe. This is really powerful. Now let's look at the quantum logic gates and how they work. These quantum logic gates are also mind benders, and it's really amazing how they work. So first, let us look at how classical logic would tackle a problem. Suppose you have like 2 to the power n states, and you want to evaluate them as an input and look at the output. So classical logic will take one input after another and execute the logic and give you one definite output. So now if you want to evaluate 2 to the power n inputs on this classical logic, you have to do it one by one like this. And this will be done in a serial fashion, and there is no way you can do them simultaneously. So you have to do all these 2 to the power n evaluations to know this logic. However, in a quantum logic gate, you can, in principle, like use a superposition of all these 2 to the power n states as the input, and it will evaluate all these states simultaneously and give you the output. The output is going to be another superposition state of all these 2 to the power n states, and it contains the information of all these executions on these individual states. So this is a massively powerful tool that you have in quantum computers. This is known as the quantum parallelism. It basically it can evaluate all the inputs simultaneously at a go. Wait a second, but I mentioned that when you measure the quantum state, it will collapse it in one of those states that you have. Like it will collapse it either 0 or 1, and as you have more and more qubits, it will collapse in one of those states like 0, 0, 0, 1 or something like that. So that means even you have evaluated all these input states simultaneously, once you measure, it is going to give you only one of these states. And if you want to know the exact output state, I mean the exact superposition state that you have, you need to have a large number of measurements on that output state. And this is going to be an intractable problem as the number of qubits increase. So are we doomed? No. By using clever quantum algorithms, it can be shown that you can still like exploit the power of this quantum parallelism. So how does it work? So you just pool right strings, and by that you can exploit the power of this parallelism. So for example, take this example of unsorted database search, and you can write down a clever algorithm in such a way that it will amplify one of the states, the probability of finding it in one of the states. But the probability of finding it all other states are going to be diminished. Now, this particular state could be your solution, or the solution of the problem that you are looking at. So this is basically called the amplification of the spatial state. And when you do that, at the measurement, you will collapse the state, or you will measure the state, and you will find it in this particular state because this probability is very close to 1. So then by measuring, you are actually finding the solution. This algorithm is basically used to to solve this problem of unsorted database. And this was actually shown by the scientist Love Grover in the early 1990s. And since then, we have tons of other quantum algorithms which can exploit such quantum parallelism. And then you can use it to make very powerful quantum algorithms and solve problems which are almost impossible to solve in classical computers. So now, how would you make a quantum computer in the lab? Like, how would you make it with a physical system? So for that, here's a list of requirements. So you need to have a quantum two-level system that will be your qubit. So you can isolate two levels from a series of quantum levels that you have. It can be an atom, it can be several other platforms. You just need to isolate the 0 and 1 of those like quantum state that you have. Now you need to be able to create arbitrary state. So that means you need to be able to manipulate this qubit, and you need to be able to measure the quantum state at the end of the algorithm. So you have this quantum states, you apply some quantum logic, and at the end, you need to be able to measure it. And finally, you also need to couple many qubits. That means you should be able to entangle several such qubits in order to have this quantum advantage. Now, based on these requirements, there are several such platforms which can be used to make a quantum computer. For example, there are superconducting circuits, ion trap, where the ions are trapped in a potential, and then you can manipulate the electronic levels of those ions to make your qubit. There is silicon qubit, where you manipulate the spin of an electron, and that is your qubit. You can also have photonic qubit, where the photonic state or the polarization of the light is used as the qubit. So here, like in our lab, we work on superconducting circuits, and I'll focus on this particular platform for the rest of the talk. So superconducting circuits are nothing but quantum oscillators. So you have all heard about oscillators, and the first thing that comes into our mind if someone says oscillator is simple harmonic oscillators or a pendulum. However, you can also have electrical oscillators, for example, a parallel LC circuit, and this is precisely what we have for superconducting qubits. So if you can quantize such electrical circuits, this parallel LC circuits, what you will have is a parabolic potential. And you know that the levels of this quantized electrical oscillator is going to be equally spaced. So all these levels are spaced at this h bar omega. And we use the 0 state or the ground state and the first excited state of this quantum system as a qubit in superconducting circuits. However, there is one problem here. You can't really access the first two levels of this system. That means you cannot really isolate these two levels. Why? Because all these levels are like equally spaced in this energy landscape. And once you try to shine light to manipulate one of these levels, this is going to be in resonance with all other levels, and this population is going to be there on all the states. So it ends up populating all the states that you have in the system. So this is just by itself cannot be used as a qubit. So what we need some nonlinearity in the system. So what we have here is called a Josephson junction, which is a nonlinear inductor. And if we replace our inductor in the system with that Josephson junction, you have a potential which looks like this. It's a cosinusoidal potential. And then the first two, the difference between the first two levels is now sufficiently different from the transition energy of higher levels. And that allows you to selectively excite only these two levels. And this isolated two-level subspace is the qubit in a superconducting circuit. Now you can manipulate the population of this two particular state, and by tuning this amplitude, length, and the phase of this microwave pulse that you use, you can actually create arbitrary state on the qubit. So remember that this transition frequency that you can design using electrical circuits are in the microwave regime, and that allows you to use all the well-developed microwave engineering knowledge that we have to just use them and like get our quantum computers work. So here is how it looks like in a like real circuit. So here is a lateral capacitor pads on a circuit, and here if we zoom in here in this narrow part, this is the nonlinear inductor or the Josephson junction. So Josephson junction is made by sandwiching a thin layer of insulator between two superconducting plates. And this is what it is. And the whole thing is now the parallel LC oscillator, the nonlinear LC oscillator, that is the qubit in our system. Now, there's one more important thing, that you know that any oscillator is susceptible to damping. So if you have some resistance or dissipation in the system, if you set an oscillator to oscillate, after some point, it is going to damp the energy. Basically, it's dissipate the energy in the environment, and it's going to settle down to the ground state. So that means it is bad for your system. So you store the information in the one state. After some time, it's going to decay back into the zero state. So you don't want dissipation to be present in your system. So use superconductivity so that it's like ultra low dissipation system, and you have a larger lifetime for these qubits. Finally, there is one other thing to look at, which is the thermal excitation. So now, if this qubit is sitting at a hot bath, that means like if it is sitting in a hot environment, the environment is going to randomly kick the system into higher excitation state. And these processes are random, and you don't want such random process to present in your system. So you want to cool down the system to such a degree that these excitations are exponentially suppressed. So for that, you first find out the energy of these transitions, and then you sort of find out the temperature equivalent using the energy equivalence. And then you find out that this temperature is roughly 240 millikelvin. So if you operate at roughly 1 order of magnitude lower than that temperature, all these excitations will be exponentially suppressed by Boltzmann law. So for that, we need a system which is capable of cooling down these qubits to such a low temperature. So this is a dilution refrigerator, which is capable of cooling down the system to a temperature of 20 millikelvin. We use that to carry out all our experiments. Here you can see that all the quantum experiments that are going to happen is at this stage, which is cooled down to such a low temperature. Now, to protect the qubit from the environment, we put it inside a cavity, as shown in this picture. So this is one waveguide cavity, and here this is the qubit that I mentioned earlier. So the cavity protects the qubit from the environment, but in addition to that, there is an interesting property that like shows up if you put this qubit inside a cavity. Now the cavity frequency is going to depend on the state of the qubit. So that means the cavity resonance will be different depending on whether the qubit is in the zero state or in the excited state. So you can use this property of the cavity to measure the qubit here. And this can be measured using, again, microwave signals. Now, this cavity doesn't have to be a 3D waveguide cavity as I shown here. It could be as well the planar CPW kind of cavity. Like you can see the CPW resonators here. And all the scalable like quantum processors that you see these days, like the chips of IBM and Google. So they use this 2D coplanar waveguide as the resonator for this qubit. So now let's come to the wiring and the control and measurement electronics of such qubits. So this qubit is now sitting at a very low temperature of 20 millikelvin, but you need to send the signals from a room temperature, like all this, like the control tone and the measurement setup that you have is at the lab, and that is at room temperature. So you need to be able to filter out all the noise and unwanted signals that are going to travel to the qubit. And for that, you need attenuators, reflective filters, lossy filters, circulators, and isolators. And when the signal is now going to come out from the qubit, it's a very tiny amount of signal. So you need to amplify the signal such a way that it's not going to be affected by the noise that is present at the room temperature. So we need all this microwave, like knowledge of microwave engineering and a clever design of microwave circuits in order to able to manipulate and measure the qubit. Also, you need magnetic flux lines and coaxial cables to connect all these components. You need radiation shields so that like you don't have any random photons just going into the qubit and do some random stuff. You need magnetic shields so that any spurious magnetic fields are now suppressed. Now at room temperature, you need continuous microwave source to generate the signals for these qubits. You need arbitrary from generators, microwave components to up convert and down convert signals. And you need digitizer to sort of analyze the signal that you're getting from the qubit. And all this is done with classical computers to control and the signal process like this measurement and the manipulation that you do on the qubits. So all this is for one qubit, but for a quantum processor, you need many of such qubits. So how do you couple multiple qubits? The principle is very simple and essentially to that of coupled oscillators. So you need to have some coupling element between the qubits. In electrical circuits, the simplest way of coupling two oscillators is via a capacitor. However, there could be several other coupling elements. It could be an inductive coupling. It could be a coupling by another bus resonator and several other things. And once you have this coupling, you can then bring the qubits on a resonance and have them interacting with each other, and then you can separate them away. And that way you can have like interactions between several such qubits. And here I present the layouts of such multi-qubit processors for the front runners of our field. So for example, this is the layout of the Google chip, where these qubits are marked with this gray cross signs. And this coupling element is shown with these blue squares. Similarly, for IBM, these circles represent a qubit. And for them, this coupling element is actually a resonator. Similarly, for Rigetti, you have these qubits and these coupling resonators. And here, like for ETH Zurich, I have actually put an image of the actual chip where you can see. So this small squares that you see is the qubit, and then each of these qubits is connected to another qubit via these resonators. These wiggly lines are basically coplanar wave resonator. And then these are some more like images of real quantum computers that we have these days. So this one particular image is from IBM. This is one of the earlier designs of Google. And this is the chip of Google that actually demonstrated the quantum supremacy recently. And now with more number of qubits, it also comes with other complexities. For example, you can see that the overhead of microwave wiring and the control electronics is going to grow as well. And there are challenges for that. So you need to be efficiently scale this cryogenic wiring and the room temperature hardware. You also need to also find compact packaging and integration for many qubits, because now the small chip need to have all those qubits, and you need to be able to talk to each of these qubits and read them out separately. And finally, the fabrication of those chips is going to be hard as well, because you need to be able to hit the right parameters for each of these qubits on a chip. And this is really a challenging task. However, the most easiest of these challenges is decoherence. And this is really a menace we are all trying to fight. And I'll explain in a while why this is so important to suppress this decoherence. So decoherence happens because the qubit is now talking to an environment in an uncontrollable manner. So the environment can exchange energy with the qubit, and the qubit can also decay through the environment. And this is a necessary evil, because you cannot really isolate the qubit, because if you like draw walls around the qubit, it's an isolated system and you cannot manipulate or you cannot measure the qubit. So in order you to manipulate and talk to the qubit, you have to have some coupling to the environment. And the same environment is going to like cause problems due to this decoherence. So this is really a very challenging task to engineer the environment in such a way so that you only talk to the qubit when you want to, and when you are not measuring anything, the rest of the environment is not actually doing some funny stuff to the qubit. So how does this environment affect the qubit? So one very simple explanation is this: if you prepare the qubit in an excited state, after some time, it is going to decay back to the ground state. This is called the relaxation of the qubit, and you all know of this as if you have some higher level in an atom, after some time, it decays back to the ground state. So it's the same mechanism. In addition to that, we have another decoherence channel, which is known as dephasing. So as I mentioned that you can prepare the qubit in any arbitrary superposition state, but after some time, this phase information of the arrow can be lost. That means this arrow is now getting all over the sphere, and that is not good for your computation, because you don't know precisely where the state is, and that way you cannot manipulate the state as you wish. So this is called dephasing. And for typical parameters, we have in superconducting qubits, both these timescales around hundreds of microseconds. So now you would want to finish all your operations at a much shorter time scale, so that you are not affected by these environmental effects. And this is a challenging task, but it is doable, because now is each individual gates for superconducting qubits can be done in a very fast time scale. For example, each of these gates can be implemented in tens of nanoseconds. So in principle, you can have tens or even 50s of gates before the system is actually going to suffer from such adverse effects. So here I'd like to mention one more important thing is the connectivity. So as I showed you earlier, the images are from the Google or IBM or other quantum computing platforms. So they use a nearest neighbor coupling in the processor. So you place the qubits in the planar grid, and then you use nearest neighbor coupling. Because it is quite challenging to have coupling in a physical system between this qubit to this one without doing crossovers and all. And once you start having crossovers, as the number of qubits grows, this like fabricating this kind of the connected network is going to be very difficult. So now how this connectivity affects an algorithm. Suppose you want to implement a quantum operation between this gate and this one, this qubit, this one sitting here. Since there is no direct coupling, you have to do it via several intermediate qubits. And that is going to increase the number of gates that you need in order to implement a particular logic. And in turn, that is going to increase the number of time you will need to implement a particular algorithm. And then you're going to suffer from decoherence after some point. So what if we could increase the connectivity? And this is the kind of problem that we are trying to look at in our lab in TIFR. And this is also part of my research that I have done for my PhD. And we have found a design which is capable of connecting 12 qubits. Here you can see, so this is like you can think of it like a 12 qubit processor, where these chips represent a qubit, and this ring actually is a coupling element that couples all these qubits to a very dense network. And we are currently trying to optimize this design and demonstrate a quantum network with high such connectivity. So with that, I'd like to thank you for listening to me. I hope I have given a broad overview of how this quantum computer work, and I hope you found it interesting. And I'd be happy if you sort of pursue on your own more, and then it encourages you to explore further in this field, and hopefully it might encourage you to join this effort to build a quantum computer. With that, I'd like to thank you again, and I'll take questions.
So there are only some few scholars who could explain this topic such beautifully and such easily that you have done using pictures and like illustrations. So I would like to thank you for explaining us the topic so well. And sure, I personally have become a fan of this right now, and I want to learn more about it.
Yeah, please write to me, and if you have any question, not right now, but if you come across any question, if you have any doubts, if you want to know something more, you want to explore some literature, you can just write to me. I think organizers have my email ID. I'll be happy to sort of entertain all such questions, and it will be a pleasure to communicate to all of you.
Yeah, sir, that's really amazing of you, and this was a really insightful talk. So thank you very much. And Anish, do you realize we are in this webinar, but we are not really in this webinar. So are we really in this webinar? So this is the time for some question and answer session. If anyone has any question, please put it in the chat box.
I would like to start with a question. So the first question is a very basic question, which will explore the basic domains of the quantum computing. That is speed the only advantage that we get while using a quantum computer? Like, can't we just increase or we achieve the speed using adding more cores to our current processors in a classical computer? So
it's not only just speed in terms of how many calculations you can do per second. It's how many steps you need to solve a particular problem. For example, I'll give you like an example of another like difficult problem that you know that is difficult to solve in classical computers. For example, you have two large prime numbers, okay? So you multiply them, that's an easy problem. So you just multiply two large prime numbers and you get a number. But now if I give you this large like number, which is a product of two prime numbers, and I ask you to find the factorization of that, so the complexity of the problem grows exponentially. So even if you have like very powerful of such computers, you can't actually solve it in a given time scale. It's not like it's growing like linearly so that you can just double your resources and get a solution. In fact, like it can be shown that for a sufficiently large prime numbers, it might take even a time scale like which is equivalent to age of universe to solve in like the powerful classical computers. So it's basically this number of states and how you sort of approach this problem, how you approach to solve this problem. So there is no simple way of doing this in a classical computer.
Thank you, sir. There is a question from Arjun. What are the challenges to making quantum computers commonplace, and what technological methods could become the way to make quantum computers common?
Sorry, could you just repeat your questions once more, like a bit slowly?
Yeah, sure. What are the challenges of for making the quantum computers commonplace? What
You mean
technological methods could we use for that?
So first, let me speculate that I don't think quantum computers are going to replace the computers that you have like in your room. So it's going to be like the resources that you need to make a quantum computers are huge. And then the first quantum computers are going to be like, they're already there. So they are basically cloud-based quantum computers. You will have your classical computers to access them. You can write down your own quantum algorithm using your classical computer, and then you can run your algorithms on a data center, not like in your home, but sitting at some other place. And then once that is run, you'll get the data from that quantum computer. So for example, this dilution refrigerator that is required for cooling down such like processes to such a low temperature is huge. You don't want to have a like large dilution refrigerator at your room, right? So that is there, but like I'd say that this technology is already becoming available, at least the primitive ones. Like, of course, you can't do much with a 5-qubit or a 10-qubit quantum computer, but this technology is already available. And if you want, I think I have a slide for that. Just give me a second. Yeah. Yeah, so we already have such platforms. They offer cloud-based quantum computing. So you can just log in, you can program your quantum algorithm and run them on their quantum computer. So in some way, it's there. If you really want to run your quantum algorithm, you can do it. But it is going to take many more years before it is like a household thing. And I don't think even that is necessary.
Thank you, sir. So our next question is, so we know that we have the upcoming technology of blockchain that we are still exploring, and since it has not become a very common technology for everyone to use. Now, if we add a viewpoint from a quantum computing domain, do you think that quantum computing might be the end of blockchains, given that quantum computing harnesses the power to destroy the cryptographic algorithms that we have right now?
Well, I am not an expert of like quantum cryptography, but I can I have done a little reading. So based on that, I can say that like yes, the current cryptography mechanism that we use is vulnerable to quantum computers. So if you have quantum computers, you can in principle like break the RSA encryption, but there could be some other encryption that could be unbreakable by quantum computers. And more importantly, quantum quantum properties of such matter offers you quantum key distribution. So this is basically quantum cryptography, and this is truly unbreakable. So that means you can't break this cryptography even with using a quantum computer. So that is going to be there. And like, as I mentioned, this like a functional quantum computer that is going to be required to break RSA encryption is still far away. Like, we don't have that yet, so you don't have to worry about that, like your ATM card being not useful yet. So there is still some time.
So as you mentioned, the next question is actually related to that. How long would it take for the world, or specifically India, to build a fully functional quantum computer?
It depends on what you mean by a fully functional quantum computer. In some sense, the quantum computer is already there. What like I could say that if you have a fault tolerant quantum computer, so that means I said that these quantum computers are susceptible to decoherence. So then you have to finish all your algorithm in a short time scale, and then still like this, that there is going to be some error in the result that you are getting. So what you really want is a fault tolerant quantum computer. And for that, you need what is known as error correction or quantum error correction. So that can sustain the quantum properties of this like states for a longer time, so that you can implement your algorithm with a very little error to any not any error at all. So, but unfortunately, as of now, so the kind of error rates that we have for individual qubits require a large number of like qubits to make one logical qubit. So there is one concept of physical qubit. So you can store the information of one logical qubit into, say, 50 physical qubits. So that number is now too large, given the errors that we come across in these current like qubits. So as this error goes down and down, and we also like sort of get more used to manipulating more number of qubits, we can have these error corrected processors, and then we can have these quantum algorithms running on them with a very little to no error in that. So that is still probably going to take a few years from now. But that doesn't mean that you can't do anything useful with the quantum computers that are there today. For example, people are already trying to do some interesting problems, for example, quantum chemistry and all, using those computers. And as you know, that like Google have already shown quantum advantage on the quantum computer. But it is not a very useful problem. So, but they have shown that this particular thing cannot be done in a classical computer faster than this. That is some demonstration of advantage, and this is, it's not like a step function that we didn't have quantum advantage and then suddenly we have one. It's going to grow like each year. Like each year, this machine is going to be more and more powerful, and then we will have better and better quantum computers.
Thank you, sir. Moving on to the next question. Uh, do we at the present have any storage devices, particularly storage devices that could be using qubits? Or do any devices exist, or do we even need the technology for of qubits for storing information?
Just for storage, I'm not sure, and I don't think you require that, because these qubits that we have today are like prone to errors. Like it will be a crappy storage anyway. So since we have like already well-developed storage for classical like bits, so then we don't need this for just storage. However, if you want to run quantum algorithm, you need to transfer those things into the quantum memory, and then use the quantum algorithm on that quantum memory, and then you have the result. Then you can transfer it back to the classical computers. So yeah, I mean, I am not aware if we have even like for a proof of principle this quantum storage.
So we'll be addressing the last question of the session. And this one's a personal question from my side. So I had a chance to go through your Instagram page, which features your paintings and your sketches as well as photography. So I would like to ask, how do you manage your time between quantum computing and as well as your hobbies such as painting and theater and football and your pastimes?
Well, it's a non-academic question, but I'll be happy to take that. So it's more like how the life of a scientist is, and it's not as hard as it appears from outside. I can say like we have all kind of fun, and yeah, I mean, and the most useful thing is like you can work on your own schedule. Like it's not that we have to go to lab at 9 and like exit from there at 7. There is no such timeline. So I used to work at like all odd hours. Like I used to wake up at 12. Then I went to lab, worked till the evening. Then I went for football. Then came back, went to lab again. And I mean, it also is a good training for you for like managing your time better, I think, because you can automate many of such things, and then you don't have to sit in front of the computer and like do the actual thing. And like you can automate such things, and then when these things are calibrating, and then you can like have a coffee, you can like visit places, you can play football, you can draw, sketch, dance. Like many of my friends are like have many other hobbies, and they're all like beautiful scientists. Like they do amazing works, and they all manage these things quite nicely. So I'd say like consider considering all these things, you must give it a shot. Like why don't you pursue being a scientist? Like it's a nice thing to be if you have the passion.
Thank you, sir, for answering all of our questions so lovingly. So this brings us to the end of our event. We hope this webinar helped you learn something new today. We express our heartfelt gratitude to Hazra sir for gracing MindSpark'21 with your eminent presence.
Thank you.
I would like to thank Dr. B.B. Ahuja, the Director of College of Engineering, Pune, Dr. M.S. Sutavane, Deputy Director of COEP, Dr. P.R. Zamangavkar, Associate Dean, Student Affairs of College of Engineering, Pune, Dr. Mrs. Aarti Petkar, Faculty Advisor for MindSpark'21, for their valuable guidance and constant support. I would also like to thank all faculty mentors of MindSpark'21 for their support. I would also like to express my gratitude towards Digital India and AICT for their support as patronage for MindSpark'21, and we are looking forward to their continued support. Lastly, I would like to thank the audience for their interest and their attention, as well as their interesting questions. Thank you very much.
We look forward to seeing all of you in all of our future events and experience the thrilling ride of MindSpark'21 and join us to realize the curing Mercury vision. Stay tuned for the next episodes on our social media handles. Sir?